Hi, so this is a talk for the paper Trapdoor DDH groups from pairings and isogenies. This is a joint work with Peter Kutas and Christophe Petit from the University of Birmingham, and myself, Javier Silva from Universitat Pompeu Fabra in Barcelona. And to introduce the topic, I will start by recalling two very well-known problems in cryptography, which are the Diffie-Hellman problems. So let G be a cyclic group, and in this talk we're going to write all groups additively, and let's fix the generator P. So first, the computational Diffie-Hellman problem is given the generator P and two other elements AP and BP for some A and B random integers. We're asked to compute ABP. And the decisional variant, we are given the same information, but also some CP, and we are asked to tell whether C is the same as AB or is some other random integer. So these problems are believed to be hard for certain groups, and they have been studied extensively without anyone being able to break them. And they have been used to build countless cryptographic protocols over the last few decades. A way to solve in some other groups the DDH, the decisional Diffie-Hellman problem, is to use a pairing or bilinear map, which is just a map from the group times itself to some other group, which we don't really care what it is right now. But what is important about this pairing is that it has a nice property, is that essentially you can move coefficients around. So as you can see here, you can move the coefficient x from the first to the second input, and you can also take it out of the pairing altogether. So given this tool, given this pairing, what we can do to check a DDH instance is to check the following equation. So we check E of AP and BP, and if C is the same as AB, then this will be the same as ECPP. Otherwise, we conclude that C is something different from AB. And thus, DDH is an easy problem when we have a pairing available. And notice that the pairing does not seem to help when trying to solve the computational version, the CDH problem. So the motivation for the idea of Trapdoor DDH is the question: what if only one party can compute the pairing and the others don't? So here's the notion of Trapdoor DDH group. It's a setting in which there's going to be some trapdoor information that allows a certain party to solve DDH instances. But without this extra information, DDH is still hard. And moreover, the computational version is going to be hard given the trapdoor. So as for previous constructions in this line of research, there's essentially two papers. One is the Dent and Galbraith paper from 2006, which introduced the primitive, the notion of Trapdoor DDH. And they provided two constructions. One of them is currently broken and the other still stand. But they were based on curves over RSA rings. So set n for n some product of two primes. And then a few years later, Sarang in 2013 introduced a new construction, which was not based on this idea of hidden pairings at all. It used a different approach. But again, it was using composite modulus. And these two papers also discussed a few limited applications, and there's some other paper that found some other applications for the Trapdoor DDH, but nothing major so far. And in particular, Sarang presented the following open problem with the hope that when someone solves this problem, when someone is able to find some construction verifying these properties, then better applications will come to light. So what he asked for was a trapdoor scheme, a Trapdoor DDH scheme in which the group order was prime and public, and at the same time we were able to hash into the group. So that's what we were set out to do. we're going to try to see if we can build something that verifies these properties and what we can do with it. So before I go into the constructions themselves, I need to introduce a bit of background about elliptic curves and isogenies. And I'll try to keep it very minimal, but I think a bit this is required to understand the constructions. Then I will briefly discuss the other contributions that we have in the paper, and finally I will conclude. So elliptic curves over a finite field are sets of solutions of equations of this form: y squared equals x cubed plus ax plus b, where a and b are coefficients in this case of a finite field. And to these points we are going to add one more that is called the point at infinity. And this is going to act as a neutral element because together with this point, the curve has a group structure. In particular, we are going to denote for some integer m, we're going to denote the m torsion of the curve, so the set of points that are killed by multiplication by m, by e bracket m. So now we have elliptic curves, and we need maps between them. So isogenies are essentially rational maps between the elliptic curves, which also fix the neutral element. And because it's an algebraic map, morphism, we can talk about its degree. So given any isogeny from E to E prime, there's another isogeny going from E prime to E, which is called the dual isogeny, which is not the inverse, but almost, in the sense that the composition of the two is a scalar multiplication by the degree of the isogeny, by any of them, by the way, both of them, an isogeny and its dual, have the same degree. And endomorphism is simply an isogeny from a curve to itself, so E equals E prime. And the set of endomorphisms actually forms a ring under point-wise addition and function composition. So we can study this ring, and actually we can classify elliptic curves in two types based on the shape of its endomorphism ring. So in the most common case, an endomorphism ring is an order in a quadratic imaginary order. In the other case, the endomorphism ring is a maximal order in a quaternion algebra, and in this case we say that the curve is supersingular. And this is the case that we will focus on, and mainly the most interesting case in isogeny-based cryptography. And one of the reasons is that it has a very interesting isogeny graph. So let L be another prime different from P, and typically L is going to be a small prime and P a big one. And we consider the following graph, which we call the supersingular isogeny graph. So as vertices, we're going to take all the supersingular elliptic curves over fp squared up to isomorphism. So if they're isomorphic, they're in the same vertex. And the edges are going to be the isogenies of degree L between these curves. And this graph, as I mentioned, has very, very nice properties. So for once, you can travel in the graph, so you can take a path, which means computing an isogeny efficiently, as long as the degree of the isogeny is small or power smooth. And the graph is what is called expander, which intuitively means that it has lots of paths. So it has high connectivity, and there's always a relatively short path to go from any given point to any other point. So as a consequence of this, we can take random walks, and the end vertex of the walk is going to be statistically indistinguishable from uniformly random, which means that we can start from a fixed point and take random walks, which are going to be efficient and in essentially uniformly random places. So isogenies come with their own set of hard problems which we use in cryptography, and the main one is the L isogeny problem, which is given to elliptic curves in this graph, to supersingular elliptic curves. We try to find a path So that's an L power isogeny between them. And very related to this, there's the problem of the endomorphism ring computation, which is given an elliptic curve, find its endomorphism ring. These problems are believed to be hard, even against quantum computers. The best known algorithms are exponential or sub-exponential in some cases. In particular, the endomorphism ring problem is easy in a certain subset of curves, a very small one, but this is actually very useful. In most protocols, it is worth, either for efficiency or functionality reasons, to start from a curve with an easy endomorphism. And these have gained some attention in the last decade, and lots of cryptographic schemes have been built around these problems. So moving on now to the core idea of this paper, let's consider the veil pairing, which is a pairing from an elliptic curve to the group of mth roots of unity. And this pairing has a property of being degenerate, which means that if you try to compute the pairing of two things that are collinear, you just get one. So if you think about the case of trying to solve the decisional Diffie-Hellman problem, we were trying to compute the pairing of things that were collinear. So we're trying to compute on one side AP, BP, and the other side CP and P. So the pairing is always going to give us one in both sides, regardless of whether C is AB or C is random. So this pairing is not helping us to solve DDH instances. But what we can do to solve this is to use what is called a distortion map, which basically is an endomorphism such that the image of a point is not collinear with a point. So now the pairing, by going through this distortion map, the pairing is not degenerate anymore, and it can be used to solve DDH instances. And notice that in general, this endomorphism psi is going to be hard to compute because of the endomorphism ring problem. So this gives us the following idea. The idea is we're going to start from a curve E0 for which we know the endomorphism ring, or at least some non-scalar endomorphism, and let's call it psi. So because this endomorphism is publicly known, everyone can do the trick that I've just explained in the previous slide of the distortion map, and so everyone can solve DDH instances in E0. And now, because we cannot use this curve for a trapdoor DDH because DDH is broken for every party here, we're going to move to a different curve. So we take a random walk in the supersingular isogeny graph to another curve E. And now, since the endomorphism of E is hard to compute, it is not that clear how to solve DDH anymore, because we're lacking this distortion map. But what we can do, if we know the path that we took from E0 to E, is actually move the problem, translate it back to E0, where we know how to solve it. So what we do here is define another pairing in which we're taking the points back, the points P and Q from E, we're taking them back to E0 through the dual of the isogeny that we just took to arrive at E. And then in the curve E0, once there, we know a distortion map, we know a non-scalar endomorphism. So we use it, and we arrive at and we are able to define a pairing which is non-degenerate and allows us to solve DDH instances. So now it's pretty clear what we do. We reveal as a group the curve E or some subgroup of it, and we keep as a trapdoor the path we took from E0 to E, so that we are able to move the problem back to E0 whenever we want and use that to solve DDH instances. So that way only the party who knows this path is able to solve DDH instances. And because the trapdoor is an isogeny, and we have seen that an isogeny between two curves is hard to compute, then we expect that nobody else will be able to recover this path. And so the trapdoor is protected by the isogeny problem. So with this idea in mind, we built two instantiations. One is using the supersingular graph over fp squared, which has been used for longer. It's better understood, and we think that it's a conceptually simpler instantiation. But the problem with it is that we can have either prime order groups or secure hashing, but not both at the same time. So then we build another instantiation using curves over fp, and this is inspired by the seaside style walks in the graph. And here all properties are satisfied simultaneously. In terms of efficiency, both constructions are roughly the same as previous constructions by Dent Galbraith and Serran, but we have the advantage in the second construction of satisfying all the properties that we wanted simultaneously. So that was the main contribution of the paper. There's also a few other contributions, which is we formalize the stronger notion of trapdoor pairing, which actually allows us to solve some problems that are slightly harder than DDH, but well, between DDH and CDH. And this was kind of implicit already in the work of Dent and Galbraith. So what they have is not only a trapdoor DDH, they also have a trapdoor pairing. We have some partial attack on the parameters of Dent Galbraith in the context where the group order is revealed. And this is based on a factorization attack using Coppersmith techniques, which it doesn't completely break the scheme, but forces them to increase a bit the parameters. And as for applications, we have a couple. One is actually a warning against using supersingular curves in e-voting because of this trapdoor DDH thing. The content of the votes could be compromised. And another is a slight improvement on the idea scheme that Dent and Galbraith presented as an application of trapdoor DDH. Actually, by realizing this idea of trapdoor pairing, which is stronger, we managed to improve the efficiency of their scheme. So in conclusion, we have some improved constructions for trapdoor DDH, which in particular solve Serran's questions, Serran's open problems. We have some partial attack on previous constructions, but regardless of having found a construction that verifies public and prime order and being able to hash into the group, still have no groundbreaking applications for it. So this is the end of the talk. Thank you very much for your attention.